The Technical AI Safety Podcast is supported by the Center for Enabling Effective Altruist Learning and Research, or CELAR. CELAR, known to some as the EA Hotel, is a nonprofit focused on alleviating bottlenecks to desk work in the effective altruist community. Learn more at celar.org. That's CEEALAR.org. Multi-Agent Reinforcement Learning in Sequential Social Dilemmas by Joel Z. Leibo, Vinicius Zambaldi, Marc Lanctot, Janusz Marecki, and Thore Graepel. Abstract. Matrix games like Prisoner's Dilemma have guided research on social dilemmas for decades. However, they necessarily treat the choice to cooperate or defect as an atomic action. In real-world social dilemmas, these choices are temporally extended. Cooperativeness is a property that applies to policies, not elementary actions. We introduce sequential social dilemmas that share the mixed incentive structure of matrix game social dilemmas, but also require agents to learn policies that implement their strategic intentions. We analyze the dynamics of policies learned by multiple self-interested, independent learning agents, each using its own deep Q network on two Markov games we introduce here. One, a fruit gathering game, and two, a Wolfpack hunting game. We characterize how learned behavior in each domain changes as a function of environmental factors, including resource abundance. Our experiments show how conflict can emerge from competition over shared resources and shed light on how the sequential nature of real-world social dilemmas affects cooperation. Joel Z. Leibo is a research scientist at DeepMind and a research affiliate with the McGovern Institute for Brain Research at MIT. His research is aimed at the following questions. How can we get deep reinforcement learning agents to perform complex cognitive behaviors like cooperating with one another in groups? How should we evaluate the performance of deep reinforcement learning agents? And how can we model processes like cumulative culture that gave rise to unique aspects of human intelligence? Joel, thanks for coming on the show.
Yeah, thanks for inviting me.
So one of the things that you work on is cooperative AI. There's a lot of ways to steer technology in beneficial directions. Why put pressure on cooperative AI? How did you decide to do that?
I can say a bit about how I ended up in the space. So my background is in computational neuroscience, really, and I came to DeepMind, and the focus is, of course, on building general artificial intelligence. And as a neuroscientist, I want to build biologically inspired artificial intelligence. And after a while, I realized that humans actually aren't very intelligent as individuals. We're really intelligent more as groups. Almost everything that we're proud of as a species is a collective action problem, and we're really more of a collectively intelligent group. So human intelligence isn't an individual property, and that's really what led me in this direction.
Wow, that's really I think I agree with that. I think largely the things we're proud of are our collective intelligence. I think that's a really great way of putting it.
And I see it as if we want artificial intelligence that can do things like invent new technologies or be creative, then we need to think about the way humans do those things, and they don't do them alone. Like this, we have a kind of a cultural stereotype of like a lone genius that invents something just by their own being so smart and working so hard. But that's not at all how it works. Almost everything is a group effort. And when you get a single lone individual working on something, they go off in a direction that is kind of plagued by confirmation biases and doesn't end up working. But when you can kind of go back and forth with other people, you can get new places that are different from where you thought you were going to get when you started out. And I think that's how all of the advances that we care about as a species really come about. And sometimes it's at a small scale. It's like a small group innovating that way, or it could be at a larger scale. We could talk about like mobilizing the economy of a nation state to say send someone to the moon, or invent a cure for a pandemic, or these are all collective action problems, and they take collective solutions.
Yeah, absolutely. I think we're going to get, toward the end, we're going to get further into how cooperative AI is situated in like the broader AI situation. But first, the paper I wanted to talk about today, multi-agent reinforcement learning and sequential social dilemmas. This takes us all the way back to 2017, which, if you look at how many papers per day get pushed to the archive, that's like ancient history. So what was working on cooperative AI like before 2017, and how is it different from now?
I think the main thing that's happened is there was more of a separation until 2017 between the parts of the artificial intelligence community that cared about multi-agent systems, cared about game theory, was interested in interfacing with economics. Like those people did exist who were interested in that. It's just that they were kind of separate from machine learning. Like they were separate from the parts of the AI community that kind of gave us the more revolutionary advances recently. And so what happened in 2017 was just the convergence of these two things, particularly with deep reinforcement learning then being applied to multi-agent systems. And that was that was kind of a catalyst. And since then there have been hundreds of papers that do that kind of thing. Right.
So yeah, the cultural divides within just AI as a subfield, need bridges to be built every now and then, and it's cool when the convergence happens. I wonder what convergences we're waiting for right now. It's obviously an exciting time for cooperative AI because a week or two ago the Cooperative AI Foundation was announced, so it seems like we're going to see a lot more because if they have like $15 million, so it seems like we're going to see possibly an explosion in this space.
Yeah, I'm very hopeful. And that's been the trend. Yeah. I mean, there have been more and more papers and more people working in this area over the last few years.
Yeah. So what do you think is the unique selling point of computer science? Like compared to economics, compared to mathematical game theory, it's an interdisciplinary field, but like what would you say to like economists about like what you bring to the table as a computer scientist?
Well, one analogy a lot of people use is in the 17th century, all the big advances were made by people who were really experts in optics. There were, they invented telescopes, they invented microscopes, and revolutionized different, astronomy, biology, all kinds of fields. And I think kind of computer science is like the optics of the 21st century. It's going to impact all sorts of things in every direction. It was particularly here in cooperative AI. This is kind of like as interdisciplinary as you get, right? We're talking about issues that have been studied in biology for decades, as well as anthropology, sociology, political science, sustainability science, and I think we have some kind of integrative hopes here, particularly because we can do agent-based modeling. It's possible to construct models where you can bring in different kinds of assumptions that maybe were originally couched in different languages and simulate them. So it might be more possible to connect things like from different fields, right? If you had some previously some economics model that maybe has some particular strong mathematical assumptions underlying it, and those are needed in order to actually get a prediction out of the model. Now we can do things like build an agent-based model, which maybe sometimes has these strong assumptions that you would have from economics, but otherwise you could put in different kinds of assumptions that maybe were only more vaguely framed in sociology, and but still get predictions out that are comparable to the ones that you would get from the economics assumptions. So it's an integrative kind of thing. Right.
Cool. Cool. So I think I'm ready to start the walkthrough of the paper now. Does that sound good?
Sure.
So I think one of the big ideas we're going to talk about can be read directly off the abstract. Cooperativeness is a property that applies to policies, not to elementary actions. This seems to me to be like one of the major things of emphasis about the framework that this paper is going introduce. Is there anything you wanted to
it's
say
worth
just about
commenting
that at a high level?
It's worth commenting on that it's kind of from some perspectives, like maybe if you're a behavioral game theorist or something like that in an economics department, you might see it as like, well, they're taking this backward step. Like, we've built up over decades this model that's distilled everything down to the barest boned essentials of there's cooperate and defect, and you can talk about social dilemmas in those terms, and you've abstracted everything down to that. So the details of the world don't matter. You just need to figure out what's cooperate and what's defect, and then you can have models that make predictions. And we're going backwards from that. We're saying we're saying that we're going to stop doing that. Instead, we're going to think about more complex behaviors again. Like, you don't just choose to cooperate or defect. Like, you push a button that's labeled cooperate or another button that is labeled defect. Like, you have to do something in the world that is extended over time and constitutes cooperation or defection by virtue of its meaning in the world and how it affects other people, other agents. But isn't just like a button that is cooperative defect. You might not even know whether you're cooperating or defecting until quite a ways into implementing the policy, the behavior.
Right. So I want to get down into the nitty gritty about this abstraction of matrix games. Because that's sort of part of our anchor here.
And I guess I should say, what do we gain from doing it this way? Like, it's a different. It's one thing to just say, like, okay, we have a more realistic model. People will say that's fine, but the whole point was we wanted to abstract it. The reason you need a more realistic model is if you're actually getting different predictions for that you can't capture with the basic model. And I guess that's what we're going to speak about.
Yeah. I think we're going to get to that in the further questions. I just wanted to, for our listeners, in case people might not be completely familiar with game theory and normal form games.
Sure.
I want to explain matrices, and I want to explain matrix games. So, so to the listener, I want you to imagine a 2x2 symmetric matrix where each component is a tuple. Each component is a tuple of two values. And basically, the two players are row and column, right? Where row is a player that selects what row the payoff will be on, and the column player selects what column the player will be on. So if you play row and I play column, and you select one, and I select one, then our payoff is in the top left coordinate, right? Which is a tuple again. So the payoff tuple, the left component is the payoff I get, and the right component is the payoff that you get. So that's why 2x2 symmetric matrices with tuples in the coordinates are effectively games.
This is the beautiful abstracted model I was talking about.
This is the beautiful abstracted model you were talking about. And it took game theorists decades and decades, I imagine, right? To come up with these models. I mean, I guess we don't have to get into the history, but it took game theorists a lot of work to make these models.
Okay.
Right?
And the idea is that you can really capture a lot with it, right? You can say, in the real world, you might have a whole complex social interaction. You talk to someone, you say things to them. Those words have meanings, but you translate all of that into whether it was a cooperative action or a defection action when you said to them something, and then you can talk about you can make predictions from the incentive structure of that. It's a formalization of an incentive structure, really, because it says what are payoffs for choosing different actions, if given that others choose other actions.
Yeah. So I feel like you're itching to talk about empirical game theory analysis, which is a part of this paper where you map the grid world games that we're going to get into later onto these matrix games.
Well, that's a particular way to do it. But the broad idea of the field is that you can really, like, the reason to study these games is because you think that they are, capturing something about the structure of the real world. And the field got its start with, they were interested in these kinds of like security related dilemmas. Things like if if the Americans are building
Yes.
nuclear weapons and the Soviets are building nuclear weapons, are we going to have these standoffs? Or are we going to have annihilation? And it's those kind of questions got them started. And there, of course, the payoffs, you don't know the payoff. The payoffs are kind of arbitrary numbers, but you can still kind of reason about the incentive structure.
Right. And that has to do with the other important thing I wanted to introduce is the inequalities, right? So there are 4 inequalities that have to hold of one of these matrices for it to be considered a social dilemma, right? Because not an arbitrary matrix is interesting necessarily, but these inequalities help us filter them out and find the interesting ones. And these interesting matrices are called social dilemmas. The inequalities describe our intuitions about what it's like to be tempted, what it's like to be a sucker, to be greedy, or to be fearful.
Yep.
Yeah. So it seems like there's a lot you can do with these matrix game social dilemmas, and I might call them MGSDs here today, but they're called matrix game social dilemmas. So you've already talked about a little bit about the kinds of stuff you can model with these. I want to get into the specifics of where the model fails. So in what way are matrix game social dilemmas wrongfully describing interesting phenomena? I think you've said some of this already.
There's a classical thing that people say about game theory, about matrix games in particular, but game theory really kind of writ large, is that it doesn't capture human behavior when you bring them to a laboratory and ask them to play the game, right? If you actually just bring 2 people to the lab that don't know each other and you don't want them to communicate, and you set them in this prisoner's dilemma situation, they usually cooperate most of the time, which is contrary to the, game theory predicts that they should defect in that game, but they usually cooperate. And so so people could say, well, game theory is wrong or something like that. But you could be more charitable than that and say, it's game theory is kind of the language for talking about incentive structures. That doesn't mean that people act in accord with it. It doesn't really say that. And so that's what kind of one, or some people will interpret it and say, it means people are irrational or something like that. But it's a bit weird if the rational response is to do the non-cooperative thing. But that's the line of line of thinking. But I'm really going in a different direction with this paper here, and with many subsequent papers, which is it's a different departure from matrix games. So for me, I'm not like trying to make a point about people being irrational or not fit by game theory or anything like that. I'm just saying that cooperate and defect actions don't exist. They're not actions that you just choose in a single atomic moment. They're actually whole behaviors that you that unfold over time with parts. Like you move around in the world. You take objects from one place to another. You say things to people, and those things have social meanings. And whether it's cooperation or defection or not is sometimes even in the eye of the beholder. You might disagree about that. And that's what I want to capture. Like, I want to be able to have models that allow for behaviors to be cooperating and defecting, behaviors that unfold over time and space. So you can't just talk about whether you should cooperate or defect, but you can also talk about how you should cooperate or defect. Maybe there's different ways of doing it.
Absolutely. Yeah, so having a big C button and a big D button, a big cooperate button and a big defect button is just not what you're interested in.
And it makes a big difference for learning as well. Like once you're thinking about learning, then it becomes, you're not just learning like whether you should cooperate or defect, just pressing C or D. You're learning how to do it. So you can ask questions like, if the other player is defecting, can I try to learn to cooperate? What if I don't know how to cooperate? What if I accidentally defect while I'm trying to learn? These things are possible in this framework, but they're not possible to ask in a matrix game framework.
Right. So we'll talk about how you divide the set of policies along those lines a little bit later. First, I want to actually list out what's in the paper about the 5 ways the formalism ignores real-world dynamics. The formalism matrix game social dilemmas. So there are 5 things listed. 1, real world social dilemmas are temporally extended. 2, and feel free to interrupt me if you want to expand on any of these. 2, cooperation and defection are labels that apply to policies implementing strategic decisions.
Policies are like behaviors that unfold over time. I'm using reinforcement learning.
Behaviors that unfold over time. So one thing I'm curious about with this point is, are like we working towards some sort of classifier that assigns labels to policies, like a classifier that I could implement?
Well, with the point, I meant it more abstractly. That as modelers, we think of it. We should think of it that way, not as that. There's just it's you have a whole policy that unfolds over time. You're making many choices, and then we talk about it as cooperate or defect as the researchers looking at it. And then when we get into details of particular models, we do sometimes use classifiers for that. But you could do anything, and it's a choice.
I see. Interesting. Cool. So 3, cooperativeness may be a graded quantity. And this is something that's basically formalized with metrics, right? Because there's a threshold. There's the social, what's it called? The social behavior metric, or I have it written down later in the questions list. Yeah. We'll come to that later. 4,
that's how we're formalizing it, right? But I mean, just in the world, right? I mean, cooperation is you can be more or less cooperative. That's perfectly reasonable in language and in life. It's just not reasonable in a matrix game.
Right, of course. 4, decisions to cooperate or defect occur only quasi-simultaneously, since some information about what player 2 is starting to do can inform player 1's decision and vice versa. And this is very different from like iterated play in a matrix game. The last one is that decisions must be made despite having only partial information about the state of the world and the activities of other players. And so that's the last reason why the matrix game social dilemma formalism ignores real world dynamics. So
the last one might be,
zoom out a little.
You can probably capture that in some kind of matrix. So you could do that with evolutionary game theory or something. But the standard formalism makes this assumption that everyone sees everything.
I see. Of course. Yeah, because of course you could like fuzz out some of the payoffs and hide stuff, but that would be non-standard. So let's zoom out a little and say, so matrix game social dilemmas are a special case of repeated matrix games, which are a special case of Markov games. So in English, what's a Markov game?
Well, the question is just, what's the Markov property, right? That just means that you have some system that's going to evolve over time, and there's a state that is going to be fully determining what happens next at any point. Right. It's always fully determined.
Not a history, a state.
Yeah. So you only need to look at one time point to know how it's going to evolve in the future. This is the same assumption you have in reinforcement learning and in many other places.
Of course.
And so this is just the straightforward. I mean, what a Markov game is, it's a straightforward generalization of a Markov decision process, the reinforcement learning thing that matters. And the real difference is that there's multiple players now. So it's not just you have in a Markov decision process, right? You have an action that an agent issues, that an environment takes in and changes a state, which then affects a reward that goes back to the agent, which can choose and gives it another view of the state. So the agent can choose the next thing. The Markov game is the same thing. It's just that it's happening with multiple agents at the same time. So at every time point, the environment takes in multiple actions and gives out multiple states. Well, it has one state, but gives out multiple rewards.
Right.
One to each agent.
One to each agent.
You could see it that way.
So
that's the way to see it from reinforcement learning perspective. But you could also see a Markov game differently as a generalization of matrix games. Like if you come from game theory. So game theorists probably would describe it differently. They would say a matrix game is one where you have that's described by a matrix, right? So you have kind of an incentive structure saying if I choose this action and they choose that action, I'll get this reward and they'll get that reward, and you have that for all possibilities. But there's no concept of state there at all. There's no sense in which, like, if the world is in this state, that will give me these payoffs if I choose these actions, and you those payoffs if we choose those actions. So a Markov game is just adding in the concept of state, saying that, like, the world itself has a state.
Indeed.
Yeah,
indeed.
Which is just it's trying to be a formalization of how things are in the real world. Of course, everything is a bit of an abstraction, but this is a weaker one than in game theory, where you're not assuming that there's nothing in the world that can affect your how your actions and rewards will map. It's a much more kind of all encompassing type of assumption.
I see. Yeah. Absolutely.
And what we actually do most of the time is we think about partially observed Markov games, which is even more open there. So you don't actually have like agents don't know about the entire state at any point in time. They don't know what everyone else is doing. They just kind of see out of their own eyes and hear out of their own ears, and have to make decisions based on that.
Yeah, totally. So there's something called empirical game theoretic analysis, and what you do is you map Markov games to matrix game social dilemmas. And basically, when that mapping is possible, we call it a sequential social dilemma in the paper.
Yeah. I could say a bit about the history of empirical game theoretic analysis. I'm not sure if I know the original history, but where I believe it started was people were interested in poker, and they wanted to know things like, you have these kind of strategies that poker players can use. Like, you can have I'm going to use the wrong words because I'm not a poker player myself, but you could play in a kind of risky style, or you could play in a more conservative style. And they wanted to know, like, well, what happens if you have two conservative players playing against each other, or a conservative player with a risky player, or different ways of playing that feel like, different. They're not like single choices, because they're not like, in this moment you either bet or raise or call or whatever. Those are the actions, but these are like play styles. And people wanted to know, what if these play styles were pitted against each other? And so you can just do that. You have people play the game and implement those styles, and then you just measure the outcomes. You see, okay, this person won, that person lost. These are the payoffs they got, because it's money, it's poker, right? And you can empirically construct the game matrix from that. But now the actions in the game matrix are not the single actions of like raise or call or different whatever. They are the like complete policies of, I'm going to play with a conservative style or a risky style, or
right.
Yeah.
Right. Very interesting.
And so what we did, that's how you apply it to like a real world data set, right? With like people playing poker. What we just did was to simulate Markov games where we had deep reinforcement learning agents, implementing policies, and we did the same procedure there. We just created empirical game matrices in the exact same way.
Okay. So I want to get a clear sense in my head of what this mapping process really looks like and feels like. So, like, is it sort of like many to one, where like multiple different situations can be mapped to like a single matrix, or is it really more one to one?
Yeah, I mean, it's definitely it's many to one. Of course, there are many more ways of doing things in the world, and ways the world can be, than there are incentive structures.
That makes sense. That's very intuitive. And what is this like? How much of this process? I'm trying to get a sense of like what this process feels like. And like, is it like, how formal is it? Is it like an algorithm that a really, like an implementation in a computer could do somehow? I guess a data set would have to fit a specification in order for that to work. Or is it something that like economists do with like, the kind of knowledge that economists have? I guess like, how automatable is this process?
So empirical game theory, analysis in general, like when you're really using it for an empirical data set, has a kind of a theoretical character to it, because you have to decide what are the actions that you care about, like what are the policies in the world. The poker example was clear. I can't articulate it properly because I don't know how to play poker very well, but you can imagine broadly different ways of playing, like this conservative style or risky style or something, and you've chosen those are the actions of the world. Now think about it like if you're trying to model some economic phenomenon or something like that, you could say maybe the choice is like we want to have some kind of market economy decision, or maybe a more kind of centrally controlled decision that we make. And that's obviously a bit subjective, and a bit you have to draw lines. You have to say like, well, what constitutes this kind of economic decision versus this other one? And so it always has some sort of like theoretical choice from the researcher involved in doing the mapping.
Right.
Yeah.
Totally. Yeah, that makes sense. And you might have mentioned this, but would partial versus total observability, change the outcome of the analysis?
Well, that's the kind of question you can ask, right? It's so in the way in what we did in this paper, right? We were simulating multi-agent systems, and so these are artificial agents now, and you can ask what did the individual agents condition their decisions on? Like, can they see the whole world, or can they see just a small bit of it, like whatever's right in front of them, and then if things that are behind them are invisible? And you can do the empirical game theoretic analysis either way, and try to find out what's the incentive structure in that multi-agent system. And you can ask, well, do I get a different incentive structure from the same multi-agent system if I change something about it, say like partial observability or whatever?
Yeah. Okay. Absolutely.
And intuitively, absolutely. The answer would be almost always you would get a different incentive structure if you're changing things about can I observe the whole world or not. Like you can't if it's a social dilemma anyway, right? If it's a social dilemma and one of the solutions is to watch for defectors and see like are they trying to is this particular player a malicious actor that is harming the group in some way? And if you can disincentivize them from doing that by maybe punishing them or something like that, you have to detect that they did it at a particular point. So if it's partial observability, there's a whole new class of ways in which you can defect. You can like hide your defection from the others, and that becomes incentivized then. So that's a change in the incentive structure.
Right. Of course, that makes a lot of sense. So I want to talk about the social behavior metric and how it's constructed. But first, I just wanted to mention that the formal definition of sequential social dilemma given is a tuple M, pi C, and pi D. It's a tuple of 3 items, where M is a Markov game, pi C is the cooperative policies, and pi D is the defective policies. So the point is that pi C and pi D are really fuzzy sets, right? Because they're defined by thresholding something called a social behavior metric. So because it's thresholding, I think of it like a fuzzy set, right? Where you could say like, or the probability that a policy is in a set, where a policy.
You can think of it that way. It doesn't. I mean, you can also just see it as like cooperation is graded, right? It's just it is the case that my behaviors may be more or less cooperative toward you, not in a like discrete on-off kind of way, just in a more or less, and that's all it's really. Totally. It's like a way of getting that into the model. That's all we're saying.
It's a matter of degree, but you do select a threshold.
So we
ultimately
the interesting part is what it is you choose to measure, right? So in this paper, one of the things we did was we created a particular multi-agent system where agents had some kind of aggressive actions they can take toward each other. They can kind of move around in a space and they can zap each other with this laser beam kind of thing. And what we did then was what we chose for the social behavior metric was we chose the number of times they use this aggressive action. So it's like an aggressiveness metric. And we said, okay, let's just call the policies that are above the threshold in aggressiveness. Those are the defection policies. And below the threshold, those are the cooperation policies.
Great. Yep. So the social behavior, it's not one metric. Then it's like
it's a choice you make in
collection.
modeling, right?
It's a choice you make in modeling. Yeah.
It's like the meaning of, it's like how you decide what is cooperation and what is defection. Like that's never been part of game theory. That's always like in the rules of the game or something. It's like it's given before the game theoretic analysis starts. It's one of the modeling decisions you make in how you map the world into your game theory model. And this is for our sequential social dilemma modeling framework. The choice of the social behavior metric is one of the equivalent things that you do. You're deciding what kinds of behaviors are cooperating behaviors and what kinds of behaviors are defecting behaviors.
Mm-hmm. Cool.
And along what dimension?
Along what dimension, right?
Yeah.
So you contrast a prescriptive view that studies what should each agent do with a descriptive view that's studying what does each agent do. I have a quote here. Quote, "It is well known that the resulting local decision process could be non-Markovian from each agent's perspective. This is a feature, not a bug, in descriptive work, since it is a property of the real environment that the model captures," unquote. Could you say more about that?
Yeah, so the first thing to point out here is that, a lot of work in computer science is very prescriptive in the sense of, like, you're trying to build a technology or something, and so you ask questions like, does it work better than the previous one, or whatever, that kind of thing. Like, there's a state of the art you want to advance. Descriptive work is different from that. It's more about generating understanding from what you're doing. It's modeling in the sense of other sciences, right? And I remember I come from computational neuroscience, which usually is descriptive. There aren't really there's not so much prescriptive work coming out of computational neuroscience. It's rare that you have a state of the art you want to advance. It's more like you want to understand how the mind works. You want to understand how the brain works, that kind of thing. And so I see this descriptive work here as the same. Like, we want to understand how human societies work, so we're modeling them. And now the particular thing you asked about, this Markovian thing, is so the reason that from the perspective of any individual agent, the problem that it faces is non-stationary. Like, if you try to take a multi-agent system and you see it as a single agent reinforcement learning system from the perspective of one agent, and then simultaneously all the others, what you end up losing the Markov assumption there. And the reason is just that the others are learning, right? So there's something that's not in the environment that is affecting what they're gonna, how the system will evolve. It's the other players learning. And
absolutely. So it's
like your actions have a teaching effect, and that's that's not capturable in single agent reinforcement learning.
Right.
Or the way you capture it is you just say you say the world is non-stationary sometimes, and you try to adapt to that. But you can't say more than just like, okay, it's non-stationary, and throw up your hands. In multi-agent, you can say it's non-stationary in this particular way that is structured, and we can potentially have more to say about it. Interesting.
Yeah. So you proceed by simulations. You design 2 games for the agents to play. So there's the harvest environment and the Wolfpack environment. What is the harvest environment?
This gathering one. So they run around and they collect apples. They get rewarded for apples. Nothing else gives any reward to any agent here. And they also have the ability to use this laser beam, which if they hit another agent with it, then the agent that got hit disappears for a little while. And then they come back a little while later. They respawn. It's like a game.
Yeah.
And so when there are a lot of apples there, like so many apples that there's no time to eat them all before the episode ends, then they just run around and happily eat apples. And they never use the laser beam. But if there's very few apples, then they both will kind of run around and try to zap each other, so that they'll have some period of time when the other agent is gone, so that they can run around and get the apples and get them all to themselves. So you end up with more apples if you can zap the other player in cases of scarcity. But in cases of abundance, that's not the case.
Yeah, of course. Yeah. Cool. And what is the Wolfpack environment?
That one, there were 2 agents that we saw as wolves, and then there was a third agent that we saw it as like it's a prey or something, and they were all learning agents in this case. the prey was just trying to escape from the wolves, and the wolves were trying to capture the prey. And there were two ways to capture it. Like you could capture it alone, or you could capture it with the other wolf. And if they went together, then they got a higher reward, maybe because it was like, the prey was dangerous or something like that. And it would hurt them a little bit if they went alone. But if they went together, they could get it without paying any penalty. And so it's kind of you have to kind of coordinate to run around in this sort of maze-like environment to catch the prey.
Right.
And since they all move at the same speed, the prey can kind of if you just kind of follow it down a corridor, it'll get away. So you need the other player to kind of come at it from the other side.
Yeah. So you train like multiple different like reward functions, right? Like the prey reward function is a different reward function from the predator reward function.
Yeah, they're all independent agents. It's decentralized in that sense.
It is decentralized. So that was my first question is like homogeneous versus heterogeneous training. Like, do you is there weight sharing or not? Like, what do you think is more interesting and why?
So all the agents are independent in this most of this line of work, especially in this paper for sure, and in almost all the papers that we've done since then. They're just completely independent. You could see them as single agent reinforcement learners if you want. And
yeah, got it. Cool. So under empirical game theoretic analysis, what properties stand out about these two games, and how are they different?
Yeah. So the main result of this paper is that when you do this empirical game theory analysis here, using aggressiveness as the social behavior metric to define cooperation defection in gathering, and then I think it was something about like this capturing alone, like this lone wolf capture rate or something we called it, and Wolfpack used that as the metric for cooperation or defection. So when you do the analysis of both these games, you come out with the product is a payoff matrix, right? Just like in the same thing you would look at as the starting point in game theory. And what you find is that they can be the same. You can get prisoner's dilemma from both of these, and that's kind of amazing if you think about it, because these are really different games, and yet from the game theory perspective, they're the same. Like they're just prisoner's dilemma, and there's only all predictions you make from game theory start from okay, we have prisoner's dilemma, let's derive predictions from there. And yet now we've just shown like these are different games where you can have different properties. Game theory is claiming that they're going to have the same kinds of outcomes. And then we go on in the rest of the paper to show like what kinds, like in what ways does it fail? Like we look for different manipulations we can make that will push the games in opposite directions, and yet keep them as they're both still prisoner's dilemma, and yet different things get learned when you change them.
Absolutely. It's many to one. Empirical game theoretic analysis is many to one, of course.
So one of the ones that was interesting was that So in the gathering game, it's sort of the default policy is to cooperate, because it's kind of difficult to learn how to defect and shoot at the other player, right? That takes some time to learn. You have to have a better neural network. There's many things there. So the easiest thing to learn is just to get the apples. Whereas Wolfpack is the other way around, right? It's actually, in that case, it's easier to do the defecting policy to go alone to catch the prey, and it's harder to go with the other player because you have to coordinate and find them and then go together.
Of course.
So because of this difference in difficulty, you get a difference in the effect of different manipulations. Like we can use a bigger or smaller neural network, and you get the opposite direction of prediction for both. Like I think in the gathering game, you get more defection if you have a bigger neural network, whereas in Wolfpack you get less defection if you have a bigger neural network.
Absolutely. That's what I think is like what is really, really interesting about this. And I have a couple questions about it later on my sheet of questions here. I just wanted to highlight again that descriptive means like we're asking questions of the form DQN tends to behave like X in these environments, right? And according to...
Though we don't think it's about DQN in particular, right? I mean, we don't think if you pick a different reinforcement learning algorithm, it would work differently.
Yeah. And like, do you think if this paper was being worked on in 2021, like it would be DQN, or would you like do like PPO or something? Like,
I think for many of these papers, it's typical to just use whatever the current state of the art is. But I should say, they do have different interpretations a little bit, right?
Yeah.
The policy gradient methods have a very I like to see them as like habit learning in an animal or something like that, where you have some. It's very like localized to like what's happening on policy as things are going on. But if you switch to an algorithm that maybe resembles something like AlphaGo, where you have some kind of planning process inside of it, you're doing tree search integrated with a value network. It's you might interpret it differently. It's more like thinking. It's like the agents are thinking through whether they should cooperate or defect, not just like choosing their behaviors and that over time and coming to have a habit of cooperation or defection. So you can have really different algorithms that have different interpretations. The difference between DQN and PPO and other A3C is probably small in interpretation. But if you went to a more like planning like algorithm, I think you would have a very different interpretation in terms of humans anyway.
Yeah. So you said some of this already. Just in gathering, you're wiggling apple replenishment rate and you're wiggling tag out time, and you want to observe the likelihood of like emergence of cooperative versus defective policies,
So this is kind of the scarcity. This is manipulating the scarcity levels in the environment.
The scarcity, right? Yeah. So is it sort of like just policies that opt to not use the tag out functionality are like kind of fuzzily mapped to policies that that favor the cooperate button?
Yeah, I mean, they're mapped to that. Yeah, with this definition of cooperation. Right. And you see, it's a choice, right? We chose that this kind of aggressiveness metric is the right way to define cooperate defect in this map. But it's like us. We're imposing our values onto the system, right? Like this is just a multi-agent system that is optimizing reward and you're getting some behavior out, and we're looking at it and saying this is a cooperate policy, this is a defect policy. But that's also what you would do if you were trying to model a real system with game theory. You'd be saying, this action has these payoffs and has this meaning that I want to call it cooperation. Otherwise, I might as well flip it and call it defection.
Right. So you're not surprised that the social behavior metric turns out to be a function of apple scarcity and tag out time.
Well, it can be. It tells you something about the environment, right? It says that you get more aggressive policies to be learned when there's more scarcity. So abundance makes no one be incentivized to learn to be aggressive, and scarcity makes agents be incentivized to learn to be aggressive.
Yeah, absolutely. And I just want to go back one more time to about empirical game theoretic analysis. Can you say more about the procedure for extracting a payoff matrix from a grid world game?
Yeah, you train agents in the multi-agent system. You get the policies, you classify them, and then you you classify them as being, this is a cooperate one or this is a defect one after thresholding the social behavior metric, and then you play them together and you just observe the scores that they get, and you play them together in different combinations. Like you say, you take 2 from the cooperate bucket, right, and you put them together and you've got cooperate cell figured out, and then you put 2 from the defect bucket, you get the defect cell. You take 1 from cooperate, 1 from defect, then you get cooperate and defect. That's how it works.
Very nice.
So this procedure works only for 2 players, but in subsequent work we generalized it to larger numbers of players, and there's a bunch of ways to do that.
Yeah. What does that look like? Is that like n-dimensional matrix? Like,
Yeah, so it's how do you visualize it is the question, right? Because if you do it just the straightforward way, you'll end up with some kind of tensor thing that you can't really visualize well. So what we do is we usually add in more assumptions about what kind of problem we're looking at that model more modeling assumptions, really, because they're about the world. And we've also often been interested in problems where the number of cooperators is what really controls the outcome. We see that like collective action problems are a name people use for this. So one way to organize the output of the empirical game theoretic analysis is in a diagram that we've been calling a Schelling diagram. So we named it after Thomas Schelling, since he has many examples of these in his papers going back to the 1970s. The way the diagram looks is the x-axis is the number of cooperators, and the y-axis is the payoff that you get for choosing whatever you choose. There's one curve will be for choosing cooperate, another curve will be for choosing defect. And you can look at this diagram. This diagram is still a representation of the game, just like the matrix is. So you can look at it and you could say, oh, there's the Nash equilibrium. Like you could pick out all of the game theoretic properties you want from that. But it's a way of organizing the data for coming out of an empirical game theoretic analysis in our case, that is assuming that the number of cooperators is the thing that determines the outcome, and then whether you choose defect or cooperate. Those two things. So it's a binary choice under externalities. That's a way to see it. It's a general model of binary choice with externalities.
Yeah. Okay, that's really interesting. So of the three classic matrix game social dilemmas, chicken, stag hunt, and prisoner's dilemma, all three of them can be extracted from Wolfpack.
Yep. If you change the parameters in different ways, yeah.
If you change the parameters in different ways. So it's not that like a single play of Wolfpack can be interpreted as any of the three, but that's a really important distinction.
Yeah.
So this is very different from gathering.
It has a different if you see this as kind of like a it's like the spectrum of the game. It's like some kind of analysis of the underlying incentives that are possible in this game world. Then you get a different. It looks different, right? You have different kinds of incentive structures can come out by varying different things. It's a more complicated game.
Yeah. So in specifically, what properties of Wolfpack do you think lead us to observe this?
Well, one thing that happens in that game in particular is there's a lot of kind of pressure on coordination as part of the cooperation. Now, I don't know if that's what causes this effect, but it probably contributes because you can get there's like different ways of cooperating. You could try to cooperate, but then like miscoordinate and end up not successfully cooperating, and you can do nothing or whatever. And the gathering one has more, like there's more unilateral action that matters in the gathering one, because the policy, like they don't really need to coordinate. They need to, one player wants to shoot at the other player, but one player wants that to not happen, right? So it's more unilateral on both sides. That might be why it comes out simpler. Yeah.
So the third experiment is agent parameters influencing the emergence of defection. So this is agent parameters, not environment parameters, like we've talked about. So what's the goal with this experiment?
Yeah, we wanted to show here that when that you can make manipulations to agents and have different outcomes for the same game and from the perspective of game theory. So both Wolfpack and Gathering were Prisoner's Dilemma, we showed before. But we can change something about how the agents learn and get different results there. And that couldn't happen in game theory. In just a matrix game analysis, you just play the game, you have agents learning in that game, and you're only going to get whatever outcome you get, and it's going to be completely determined by the matrix. Whereas here, we're showing that if you change something about the agent, you can end up in a different result that is not predicted by the rules of the game, right? Yeah, that's the outcome of the empirical game theoretic analysis.
Right.
and the important reason for it here is this difference between gathering and Wolfpack, and like which is the easier policy. So when you make the neural networks bigger in gathering, you get more defection, because defection is the kind of harder thing to do. Whereas in Wolfpack, it's the other way around. You get less defection when you make the neural networks bigger, because cooperation is the harder thing to do.
Exactly, yeah. I have a question about that in just a little bit. But first I want to ask, I have a quote here: experimental manipulations of DQN parameters yield consistent and interpretable effects on emergent social behavior, unquote. Can you say what you mean by interpretable, and was there anything surprising to you about this?
The things we're interested in are like, how do incentive structures interact with the properties of the world? And so
yeah,
when we say that results are consistent and interpretable, it's saying that we have models that make sense, right? So we have in some cases we'll ask things like you have resources with certain properties, maybe they're you can't exclude others from accessing them, or when you collect resources, then the resources are gone, or maybe they can be enjoyed by others. Like, how does that like the actual implementation of that in the physical world affect the incentives that come out? And that's what we mean by this.
Yeah, cool. Back to the network size question. Like you said, Wolfpack larger networks seem to enable cooperation, while in gathering, larger networks seem to enable defection. Like, this to me seems incredibly important. For the whole Cooperative AI project, where we can sort of like, we might live in a world where we are like figuring out what network sizes imply what kinds of behaviors, and we're like only deploying in the network sizes that imply the behaviors we want. And this seems to me to be like very powerful, not like completely unproblematic if we're thinking like we're like projecting our values onto it, then we have like sort of an broad alignment problem there. But like, where do you see the literature going in terms of graphing the complexity of behaviors against their cooperativeness, against how large a network is necessary to model it?
I don't think network size is necessarily the most important thing in general, right? It's not clear how capacity gets utilized in networks or anything like that. But more broadly, like, you can make different choices about different kinds of neural architectures that would affect how much cooperation you get. And remember, I'm a neuroscientist, right? So I want to be able to say things that are connected to the brain, right? And we have ideas about what does it look like if you have a person that doesn't, that say, isn't considering social moral outcomes of their decisions, or doesn't care about that, but it still is in every way rational and able to think and other things. And we call that psychopathy when that occurs. And so the question is like, are there manipulations in agents that make them more psychopathic, or manipulations in agents that make them more kind of caring about others and altruistic and different things. There's lots of ways of slicing these. You could just say like, well, why don't we just make them share rewards or something like that? Sometimes you can do that. It depends on what kind of question you're asking and everything else about it.
All right, so yeah, that's basically the walkthrough of the paper. So now I want to, after the walkthrough, just get into some broader discussions. So you were a part of the document Open Problems in Cooperative AI, which accompanied a workshop at NeurIPS 2020. So in this document, there were 4 main families of capabilities research that are identified: understanding, communication, commitment, and institutions. Can you talk a little bit about that document and the path from the Marl and SSD's 2017 paper to the 2020 NeurIPS workshop?
Yeah, I can give my personal take on it anyway. I know my collaborators have had different ways that they've gone through this journey, but for us, for me, we have been considering kind of a sequence of different models asking different kinds of questions. So after the first paper, we got particularly interested in things with more of a sustainability science angle on them. We were interested in common pool resources, which is like a model of natural resources that you can either deplete or not, and have a tragedy of the commons arise or not. We were interested in asking the same kinds of like empirical game theoretic questions, like what happens if you have different multi-agent systems that live in or in environments that have different like physical properties. Do you get is it more likely to have a tragedy of the commons or less likely to have a tragedy of the commons? We have several papers in that direction, and sometimes we asked more pointed things about the agents themselves within the systems. So in one paper, we were thinking about what happens if we give them these inequity aversion mechanisms, which some strands of behavioral economics think people have. They're kind of like, it's like a model of like a envy or guilt feeling or something like that. And if you put that into the agent, then how does that affect whether you get cooperation or defection? And you can get kinds of like, if you have agents that are able to affect each other's outcomes by maybe they can zap each other and things like that, you can get sanctioning effects emerging, which can affect whether you get cooperation from these. Like, we were looking at that sort of a line of, put different things into the agents and have different kinds of environments. Do you end up with more or less cooperation, or do you get tragedy of the commons or not? And we've had, so that was, early work was kind of a bunch of different environments like that. More recently, we've been interested in trying to move it toward eventually having like a benchmark where we can say this is state of the art. This is the kind of so it's not purely descriptive anymore. It becomes something that is where we can talk about improving things over time and having different agents that are more or less developing the kinds of institutional solutions to their cooperation problems that we want. And so recently we have been working on a benchmark that we're going to release very soon with a large number of environments. And so it'll be very easy for anyone to just run. If you have a new agent idea, you can just run it on this benchmark and we'll find out. So you can ask questions like, even if it's not an idea that's particularly about cooperation, you just have some way of making agents smarter. You can ask like, okay, if I make agents smarter in this way, do they cooperate more or less? And that's, it's not clear which direction that would go.
Wow, that's exactly what I was going to ask next. If there were any like benchmark or competition ideas you had, but you're on top of it already. So I look forward to that getting released. I have a question from a listener here. Of the 4 families identified in the Open Problems document, again, that's understanding, communication, commitment, and institutions. Which do you think has the most leverage to make like cooperative AI beneficial for like humanity?
Well, institutions definitely.
Institutions definitely.
Yeah, institutions are the way that we change the rules of the game. That's how our society advances. We started this conversation talking about how I got interested in this in the first place, and I said that we want algorithms and agents that can be creative and can innovate like humans have, and like all the things that we're proud of as a society. That we sent someone to the moon. We have developed a vaccine for a pandemic. These kinds of things that are they're all collective action problems that are solved in that way.
And they're beyond playing games. They're making games.
Yeah, that's what I mean, right? So that's why institutions are important. Like, so if you just saw the incentive structure always fixed, then you have this kind of like huge exploration problem in the world where you have to just be like, well, somewhere out there I could discover this thing and it would be great if I were to discover it. It would invent some new technology or something. But there's no way to get from here to there. You could like change things randomly until you get there or something like that. But if you can instead change the local incentive structure, like we're going to let individuals, say, compete with each other to get funding for their projects or something like that, then you can get deep exploration that moves in a consistent direction, at least. And often people will tell a story like this and they'll point to arms races and things like that as the main kind of evidence for it. Like you can have competition organize how you organize the game that's being played, so you can get exploration going far away from where you start. That's how things like AlphaGo or other like self-play based systems often work for competitive games. But I think cooperation can do the same. And I think the pressures of you have a social dilemma and then you find a way to resolve the social dilemma creates new incentives for new ways of defecting. And then you have a new social dilemma and you have to have a new solution to that. And I think you get a similar effect from cooperation. And probably both are important in the world to organize innovation. And so institutions are the way in which we solve things. Like institutions are the rules of the game. So whenever we change the rules of the game, we perceive it as like a new kind of institutional choice. And
so back to the idea where learning agents are independent of one another and each regard each other as a part of the environment. This seems to me to be an interesting thing we can wiggle to sort of weaken the assumption, to open up the possibility of modeling the other agent as an agent, right? Which like would be complete with beliefs, including recursive beliefs, like of the form my model of your model of my model of you, and so on, right? Like, which is sort of touches on what I think is like the understanding aspect of from the Open Problems document. So do you expect the direction of research from weakening that assumption to be useful?
Sure. I mean, you do want to be realistic, right? We want to do artificial intelligence that is related to the way biological intelligence works, and humans can do this. I'm skeptical that humans are all that good at it. So I'm skeptical that it's a big part of human cooperation, actually. But people have differing opinions on that, of course. Some people think that if you just thought really hard about how we're about other people and have empathy, and everyone would come to a cooperative kind of would make beneficial choices if they thought harder about it. I maybe have a darker view of people than that, because I don't think people would usually come to those kind of conclusions if you just think harder. And there's evidence as well for this. Like, so there's a paper by David Rand is one of the authors, where they asked participants to make choices in one of these economic games, like Prisoner's Dilemma kind of thing, under time pressure. And they found that people, when they're more time pressured, would usually choose the cooperative thing. But if you gave them more time and they could think about it for a while, then they would choose to defect.
Wow.
So it's and I think in subsequent work has shown other things. It's like it might be culture dependent and other things. There's many caveats to that work over time, but I think it says something important about thinking, right? Like thinking, the process of thinking doesn't necessarily lead us to a place that is where we want to go. It's but the process of and like kind of social norms and habits, like these things can all be integrated in such a way that you just make choices that are cooperative automatically. And so I think institutions can be part of that, right? Institutions create the incentive structure, which is the world in which you learn habits. So you end up with a habit of cooperation, regardless of whether you think about it or not. And that's what I think we should be looking at, both for AI and for humans as well. Yeah.
So my next question is, what's your vision of the world on the default outcome if cooperative AI research is neglected? And my sense is that you think we're just going to undershoot the possibilities for AI if cooperative AI research is neglected, right?
Yeah. I mean, I think it's really, it's not so much that I think we need cooperative AI to create a beneficial outcome. I think we need cooperative AI to have any kind of AI that is meaningfully something we should call AI. And
that's a much more interesting claim. But I think it makes a lot of sense. So for you, the default outcome of cooperative AI research is neglected is just a world with like very narrow notions of artificial intelligence.
Right. Because I think invention and creativity require this ability to change the game, and that's what multi-agent systems can do, and that's what cooperative AI is studying.
Yeah. Here's sort of a darker turn. I have a quote here from Andrew Critch from Berkeley that he wrote on the Alignment Forum about multi-agent reinforcement learning in general. He writes, multi-agent reinforcement learning risks making it easier for fleets of machines to cooperate and or collude at the exclusion of humans, increasing the risk of humans becoming gradually disenfranchised and perhaps replaced entirely by machines that are better and faster at cooperation than humans. And I think intuitively, like, you know, criminals can cooperate for like antisocial goals, right? But it gets much deeper if in this sort of threat model where like the cooperation
it's really just not about
to exclude.
Yeah.
So what do you think? What do you think about this kind of critique of multi-reinforcement learning?
The point is overblown here, because it's true of all technology, right? Like, you could say literally the exact same thing. You could read out the same quote and just change, multi-agent reinforcement learning to, the telephone or something like that, and everything else. It's all true. The telephone helps helps criminals to coordinate and cooperate as well, and they do it faster. And maybe we can worry that they're going to do it faster than the good guys, but that feels like an overblown worry here. I mean, both of them, you get, technologies are neutral. You build technologies for different things.
Technologies are neutral.
Yeah. I mean, and there's another point though, which is that, I think cooperative AI research is important for understanding what can happen, because it's research that is we're modeling. It's descriptive in this sense, right? We're modeling the world that can contain malicious actors in it, and we can find out this is an effective way to build an institution that disincentivizes malicious behavior, or this is not an effective way to do it. So in that descriptive sense, then this is the only kind of research in AI that's happening now that has any chance of preventing those outcomes. But not in the sense that the technology that's coming out of it has anything to do with those outcomes. It's just that we can try to understand them in multi-agent systems that we simulate.
What is some high-level research advice that, if people followed, would result in more research that you'd be excited about?
Don't be afraid of doing descriptive work. I think that's... I think descriptive work and prescriptive work inform each other, and the best way to do both, to do either one, is to do both simultaneously.
Very cool. So I was talking to a researcher yesterday who said a lot of knowledge about how the research process is done is exchanged verbally and even spatially, like things that don't happen over Zoom calls, things that happen in the office, but moreover not written down. That there's a barrier and a bottleneck to somebody who's trying to learn to be a researcher just by reading stuff they can find online.
That's definitely true.
That's definitely true. So what's... is there anything about the research process at DeepMind that you can share, since we are talking verbally? That's something that's one of the magical, mystical, not written down sort of things that you can just kind of share briefly.
Well, in this, following on from the way we were talking about it before, it's an institution that wants to create innovation, right? Like DeepMind is hoping to build a general artificial intelligence, which is a technology that doesn't exist yet. No one knows how to build it. So the question is, how do you structure the rules of the game so that the individuals that work there will make advances toward this thing that we don't know how to build? We don't know where it is. We don't know what kinds of fields are relevant to create it. We don't know many things. And so I think one thing that's interesting about DeepMind is there's been a fair amount of experimentation in this institutional structure, like choices about what's the how teams form and how they relate to each other, and how people are incentivized within the system. And we've gone through a range of different ways of doing it, and I think that's an important thing about it. Like, institutions themselves need to be kind of open to playing around with the incentive structure to organize more innovation. And that's true not just for DeepMind. That's true everywhere, right? Like any organization that is doing a lot of innovation, I think, is probably also thinking deeply about the ways that they're organized and probably willing to do some experimentation there.
Yeah. So what do you think about like the publication process, the peer review process? Is that like a net positive institution, would you say? Is it something that you look for alternatives to, or what's up with that?
I think publication is very helpful. I mean, I think that's how it forces you to write down your ideas and understand what before you write a paper, you just have a bunch of results and you don't quite know what they mean. But then when you write it, you figure all that out. And
Right. So about experiments and about descriptive results, like, do you think, like, I mean, I get the sense that like you believe that your neuroscience training has informed the way you do experiments. Is that
yes.
Yeah, and like I'm wondering like how you decide how to present experiments, how you decide to carve down the space of hyperparameters in the first place, to choose the ones that you're going to experiment on, and the ones that you want to report, and the ones that are relevant and interesting to report on, and not just hyperparameters, but just a whole array of initial conditions. Like how do you hone your intuition about that part of the process?
Well, you need subject matter expertise. If you're trying to model a particular phenomenon in sustainability science, you have to read about that phenomenon and understand it, and see what do people in the field think. What do they what kinds of models are they looking at? What kinds of empirical phenomenon do they consider not modelable at the moment? That's how you do it. And really the best way to do it is to engage with experts, right? Who are from other fields, who are from different social sciences or from biology or sustainability related areas. Like there's a huge amount of expertise, and people are happy to collaborate and answer questions. And I think that's really the best way to do things. So it's a particular variable, right? Something about the environment, say, like, the climate works a certain way. People will have variables of interest. You ask them and you find ways to model them.
Right. So you mentioned the benchmark. What else is next for your work in Cooperative AI?
So the benchmark is a thing right now. We're hoping it'll come out by the next couple months, by ICML, probably, the conference. And it's going to have quite a large number of different environments where you can ask questions about cooperation and defection, but it's all kind of in a uniform setting, so you can just run it once on everything. The other thing that it does is it's about generalization, really, that we're measuring. So agents learn in self-play, like you kind of create a little society of agents that all play together, or however you want to do it. But then at test time, you're playing with others that you've never seen before. So it's like unfamiliar other agents in the world. That you have to generalize to. Or it's some combination of familiar and unfamiliar that we set out for each individual test. And it's a large number of tests.
Cool.
So I think that's really the right way to do this, because you want agents that are able to learn well and get high rewards, and do so in ways that we think are cooperative. In the case of different kinds of problems with that, like, there are tragedy of the commons problems, there are public goods problems, there are resources could be different ways. You want that to work across all of those possibilities, and you want it to happen, like, even if there are other agents there, and sometimes the agents are like nice agents that are going to help you, and sometimes they're like mean agents that are going to try to hinder you, and your kind of simulated society that you're creating has to be able to handle both.
So, Joel, do you have any final words you want to share while we're here?
Just that this is a really exciting area of research right now, and we have a lot of momentum. I think there's a lot of people entering the field recently. Like, there've been large numbers of papers coming out. There are workshops, and and conferences, and it's just a really exciting time to be thinking about cooperative AI and about multi-agent systems and about social dilemmas and everything in this space. And I hope more people will enter and work on it with us.
Yeah, so you're saying join us. You're saying like you're making a recruitment comment.
Yeah.
Yeah. Well, my guest today has been Joel Leibo. Thank you so much, Joel, for coming on the show.
Thank you.
Music by Alex Kulik. Thumbnail image by Max Wild.